Moving on to section 1.4. Section 1.4. Solving differential equations. Differential equations. I'll write it out because I'm a nice guy. Differential equations numerically. All right. Okay. All right, so first of all, what is a differential equation? If you're coming from, just a Calc 1 background, single variable calculus, you might not know what that is. You might, but it's nothing really that complicated. Basically, it's any equation involving a derivative, and it's usually with respect to time, especially in physics. So an example would be, imagine you had y of t equals d dy dt. Then this is a differential equation because we have a function and we have its derivative in an equation, right? Now the goal of a differential equation is to solve it, and what that means is to find out what y of t is, besides its relationship to its derivative. So, in our case, y of t is pretty straightforward. It's just going to be some constant times e to the t. Now, why is that? Well, that's because if you differentiate this function with respect to t, we find that it's simply this. And now we see that y of t equals dy dt. So this function, ce to the t, satisfies this equation, this differential equation, right? So that's an example. Let's do another example. So in physics, we have our equations of motion, such as F equals ma, or tau equals moment of inertia times alpha, angular acceleration. For example, if you have a falling object in free fall, your ma is equal to negative mg. And of course the m's divide out, and we know that a is, say, dy second dt second. So what we have here is y, and I'll write double dot, where double dot means second derivative. One dot, would be, so I'll just put the notation here. One dot would be dy dt. So y double dot equals negative g. Okay, so this is a differential equation. Now, how do we solve it? So we could integrate both sides, and we'd get y dot, maybe plus a constant called c1 equals negative gt plus a constant, plus c2. And then I could just move this constant over, and I can call the difference between C2 and C1 C3, right? And now I'd like to know what that constant equals, right? So I could have this boundary condition and say that y dot of 0, this is the velocity at time t equals 0. We can call this v naught, or v initial, right? And if that's the case, then I plug in 0 here, we see that v naught equals c3. So now I know that y dot is minus gt plus v naught. And now I can integrate one more time. So y, plus c4, if you like, equals minus gt squared over 2 plus v naught t plus c5. And I can move the c4 over, and I get something like this. Plus c6, let's say. Now I want to know, what is this constant c6? Well, I can say that y at 0, the initial position, is, say, y naught. And so I put 0 in here, 0, 0, and I see that y naught equals c6. So y equals minus gt squared over 2 plus v naught t plus y naught. And here we have our equation of motion of the height of an object in free fall. All right. So that's all good. But there are lots of equations, lots of differential equations that don't have these nice analytical, quote-unquote, solutions. And what I mean by analytical means they don't have exact solutions, right? Now, what that means is we need numerical methods to approximate these solutions. And in other words, we need to use computers. And we can get more and more accurate approximations the more computing power we have. So now we want to demonstrate the procedure, okay? So here we have another differential equation. And we'll talk more about this one in chapter 4. But this has an exact solution, right? But we're not going to worry about the exact solution right now. We're going to see how can we solve this numerically. So if you don't know, this is the equation of motion for a mass at the end of a spring with angular frequency equal to the square root of the spring constant over its mass. And its exact solution is this. So if someone told us what these values are, in other words, if someone told us how the behavior of this system starts, in addition to how it evolves, then we should be able to determine everything about the system. Let's suppose we have a small increment in time, really small, and we call it e. And now we know that any function x of t can be written as its Taylor series expansion with a as its center and or 0 as its center, otherwise known as a Maclaurin series, right? So we know that that x of t is going to be x at 0 plus x dot at 0 times x. over 1 factorial, right? Plus x double dot at 0 over 2 factorial, x squared, right? Plus, and so on. So in our situation, now instead of t, we can put x of e, right? And so this is going to be x of 0 plus e times x dot at 0. And then, likewise, if we take the derivative of both sides of this equation, we get x dot at e is approximately equal to x dot at 0 plus e times x double dot at 0. Okay, now we have x of e and x dot of e. So we can get the next one, right? So now we can get like x of twice e. And that should be the previous one. So now we have this, we have an approximation now. So now we have x of e, and to get x of the next increment, we just look at the last one, right? Same for its derivative. And you can do this to get all of time, right? So in general, x of t plus the next increment is equal to the last increment. I should say it's equal to the position at the last increment plus the increment times the derivative at the last increment. And likewise, same could be said about first derivative and its relationship to the second derivative. Okay, and you might be wondering, like, okay, but we were never given x double dot, right, of e or whatever. But actually, we were, right? We know that x double dot of e or any t for that matter is minus omega squared times x of t. So whatever, if it's e twice e, you can just plug it in here, and we already have this, right, from this. So we should be good. All right, so now let's look at an example of this. Let's suppose that a particle starts from rest, right? So that means x dot at 0 is 0. And let's say x of 0 is 2. It starts at a position of 2. Okay, and I'm not going to include any units because now we're going to write code for this. Let's say that omega squared is 5. Okay, so we'll use some notation in our code. We'll say x1 equals x dot, and let's say x2 in our code is x double dot, and we'll say, you know, e is e, and then yeah. Let's write up some code that we can run that'll accomplish this, right? So let's set up our initial position. I'll say x equals 2, and then I'll say x1 equals 0, right? The initial velocity. Then I'll say e will make something small like 0.01, and then we'll do like a loop. So maybe 300 should be fine. And then here we have the second derivative. This is from our given differential equation. -5 times x which we have as 2 for now, and then it'll evolve, right? And then x will evolve by an increment, right? So it'll be x what it is. It'll be what it is now plus e times its first derivative, right? And then not only that, but the first derivative will equal what it is now plus e times the second derivative, right? And that's it. And we could maybe, just show what x is, right? So let's see how that runs. I guess Python 3, right? Okay. This is at time t equals 3. This x. 3 because 300 times 0.01 is 3. So this is like 3 whatever. Right, so of course you're not going to get the exact answer for x, but we'll get a pretty close approximation, and that approximation again will get closer and closer as e goes to 0. In fact, it will be exact when e goes to 0, as the limit goes to 0. So, and that's how derivatives work in the first place, and that's how the Taylor series works in the first place. But so let's try that, right? Let's see if we can get this to be even a smaller, and then of course we'll have to increase this by a factor of 10, and we'll see the change in our answer. So it is slightly different, right? So it does make a difference. So now let's try one more 0. And we're getting closer and closer to the real result, right? So now, going back to our exact solution, the exact solution is this here, right? So our amplitude, in this case, our amplitude is going to be, so I'll say x of 3 is going to be, 2. Our amplitude was 2, and then cosine of omega, which was square root of 5. And then t. So we plug 3 in here. I'll put 3 now. This will give us you'll get something like 1.822. You see that? So we got pretty close. All right, let's get some problems in. So let's try this one here. Let's try 2 masses, 1 swinging. This is what we're looking at. So here you have a mass, and then you have another one, equal mass. And it's got some angle with the vertical theta. So we have our equations of motion given to us, and it's a problem in chapter 6. We might do it, but here are the equations of motion. So, yeah, it looks like R is this. So R is the distance that this mass is from this pulley. both masses start out at rest. So that means that our r dot of 0 is going to be 0, right? With the right mass making an initial angle of 10 degrees, pi over 8. So theta at 0 is going to be 10 degrees or pi over 8. If the initial value of r is 1 meter, so that means r at 0 is going to be 1 meter. How much time does it take for it to reach a length of 2 meters? So r of t is 2, right? And of course, g is 9.8 meters per second squared. So we're going to write a program now to solve this numerically, right? All right, so I'll go ahead and pause the video here. Try this one on your own. You can go ahead and use whatever programming language you feel comfortable with. I'm going to use Python. In the last example, we used this kind of iterator. This time, I think you'll find it more helpful to use a conditional loop, right? Like a while loop. So just think about what that condition is, and it should be good. Let's create a new. So this is 117. Okay. So we're gonna do it. We're gonna follow this kind of protocol. It's gonna give us the. Well, it's gonna give us the position, right? But we need the time. And we already have the position. So what can I do? Well, if I already know that it's 2, I can get the time, right? I'll just stop the program when x equals 2. Right, so we'll put our initial conditions in. So I'll say that r equals 1. And I'll say the first derivative of r is 0. And then I'll say e equals 0.001. That seemed to be a good number. And then for I in range, and we don't know. So why don't we just do while r is not equal to 2. Well, the thing is, it won't be exactly 2, right? Why don't we say like while r is less than 2? Yeah. We'll say the second derivative. So here's our differential equation now. Oh, okay, yeah, well, we can just divide by 2. Okay, R2 is going to be R, which we have, times theta. So I'll say theta 1, right? Theta 1. So we need theta 1 then. So we need theta. Theta is going to be 10 degrees. I don't know if this takes degrees or radians. So let's find out, right? So we know that cosine what's the cosine of 90? It should be 0, right? Oh, we need math.cosine. We need to import math. Okay, so it's in radians, right? So we're gonna need pi. So it should be, then if we want 0, it should be pi over 2, right? So maybe math.pi over 2. Okay, that's basically 0. Where was I? So theta is gonna be, so we want math.pi over 8. Math.pi over 8. And make sure these units are right? So this is a meters per second squared. And, you know, this is 0, and then this is seconds. And that's fine. That's good. And then, okay. All right. So now back to our differential equation. So R2 is going to be R times theta 1. We don't have theta 1 yet. So theta 1 is it's from rest. So again, that's 0. And then now we're good. So theta 1 squared, and then this whole thing divided by 2, right? Each piece divided by 2, so g over 2 now. Oh, we need g, right? So let's say g equals 9.8. G over 2 times 1 minus cosine of theta. Math.cosine. Okay. And now we should probably just update theta 2, right? Theta 2, yeah. Okay, so theta 2 equals negative 2 times R1, which we have, times theta 1 over R minus G times sine, math.sine of theta over R. Okay, so that looks good. And now we can use our Taylor series approximations. So R is going to be R plus R equals R plus what? R equals R plus E times R1. Not only that, but R1 equals R1 plus E times R2. All right, not only that, but theta. So here's our double primes, here's our R's, and then here's our theta. So theta should be theta plus E times theta 1. And theta 1 should be theta 1 plus E times theta 2, right? And this will update these guys. Now I want the time, right? So I have E, right? That keeps track of, well, that doesn't keep track of time, but I could use that to keep track of time. I could say, you know, I could keep some kind of record of E, right? So I'll say time. Time is does time start with 0 or it starts with E? It hardly matters, right? I guess it starts with 0, yeah. And then once we use E, time is now at, or maybe when we're about to use E, time is at E, right? So time, I'll say T. T equals T plus E. I believe in Python you can do this, plus equals E. And now we're going to print E. I have about 3.65, about almost like 3.5 seconds. Oh, it's pi over 18, not over 8. Okay, 8 seconds. Cool. So let's try another one. All right, let's try problem exercise now. Exercise 1.17 pendulum. All right, so we have a pendulum of length L. It's released from the horizontal position. So something like this. It's released from the very horizontal position, right? So that means that theta of 0 is 90 degrees, or pi over 2. Right? It can be shown that the tangential, and it has a length L. Okay, so actually I don't know why I put dotted lines. I'll just put a straight line there. And here's the vertical. Okay, this is 90. But this is L right here, okay? And it can be shown that the tangential, F equals ma equation. So that means that the tangential acceleration, right, is where theta is measured with respect to the vertical. So apparently, theta double dot is minus g sine theta over L. So this is your differential equation. Now we're going to suppose that L equals 1 meter. And of course, g is 9.8 meters per second squared. Write a program to show that the time it takes the pendulum to swing down through the vertical position. So that means once theta is, so when theta is 0, show that t is going to be 0.592. All right. So doesn't seem that bad. All right, so go ahead and try this exercise on your own. You can pause the video right here. All right, and for this exercise, I'm not going to provide a hint. I feel that it's honestly just the problem we just did before this, problem 1.7, but honestly just easier. So just apply what you did in problem 1.7. Import math again. So we have our initial information, right? So this time it's all about theta. So theta is, as we said, 90 degrees, which is math.pi over 2. Theta dot, this is from rest, so 0. E, we'll say, is 0.0001. And then theta, I already have theta. Okay, and then I already have theta. Oh, I don't have theta 1. Oh, I shouldn't write R1. I should write theta 1, right? Theta 1. Okay. Of course, we have G, which is 9.8, and we have the time, which is 0. Okay. Now, while theta is greater than 0, right? We have to make sure theta is being subtracted. But it is, because theta double dot, right? So so we have so theta 2, right? Theta 2 is going to be minus g times math.sine of theta divided by L. I forgot about L. L equals 1. Okay. And what else? Then we have our little t plus equals e. And and the updates now, right? So now theta is theta plus e times theta 1. And not only that, but theta 1 is theta 1, theta 1 plus e times theta 2. And I believe that as time goes forward, theta should diminish, right? Because e times theta, so theta 1 is 0 for now. So theta won't change, but theta 1 gets updated. And how does theta 1 get updated? It looks like it's old 1, but then it gets updated by theta 2, and theta 2 is a negative number, so it should get smaller. Theta 1 should be negative, and I think this should work, but hopefully we don't get stuck in the loop or something. So I'm going to print t, and we want to show, we're expecting, what are we expecting? We're expecting 0.592. This is problem 117. Yep, there you go. All right, well, if you enjoyed this episode of this lecture series, go ahead, drop a like. Really appreciate it. If you have some kind of sick desire to keep up with the series, go ahead and subscribe to the channel. If you have any questions about what we did here or anything really, leave a comment. And last but not least, if you think you might benefit from my tutoring services, feel free to scan the QR code you see here on screen. That will set up a 15-minute free consultation with me. If you're struggling in whatever math or physics class you might be taking, I'd be happy to see if I could help you. And with that, peace out.